Okay, in this video, I want to introduce you a new concept about sequences. So sequence is a list of numbers, and we want to be able to talk about limits of these sequences and what happens if we had an infinite list of things that we want to add together. Let's jump right in. Okay, all right, let me go to the right page. Okay, so what are sequences? So a sequence is an ordered list of numbers. So it's not just a list, like each item on the list has an order to them. So this is the third item, and this is the fourth item, and so on. So you make a list, first term, second term, third term, nth term. So list could be finite, where it ends at a particular term, or it could be infinite. So it could go on forever. And most in this class, we're going to be dealing with infinite sequences for the most part. And how do you write down an infinite sequence? Well, you can't just list them all because it doesn't fit in a piece of paper, no matter how large. So you might have to describe them by how these numbers are generated. It could be a formula for the nth term, or it could be a formula to get to the next number given the previous numbers. Okay, but either way, when we have a sequence, we might write it something like this. So we might use curly braces to denote that this is a sequence. The name of the sequence might be coming here. So here, A sub n is the name of the sequence. So A is the name of the sequence itself. And the subscript n is the nth term, right? So typical nth term looks like this. On the subscript, outside of the curly braces, you might write down the starting index. So here n equals 1, denoting that the sequence starts at n equals to 1. I know there's a lot of computer scientists in this class. A lot of computer scientists like to count from 0 instead of 1, right? So that's perfectly fine sequence. We could say starting from n equals to 0. It doesn't have to be 0, 1 either. You could start with 27 if you liked, or negative 99. But the starting index comes with the subscript, and the superscript tells you what the sequence goes up to. So if it's a finite sequence, you list the largest number term, maybe it's 100. Or if it's an infinite sequence, you write infinity here. Okay, so let's look at a couple of examples. This might be a sequence. So this time formula was given inside of the curly braces. So this is a sequence n over n plus 1. The nth term could be gotten by a fraction with n in the numerator and 1 bigger than that in the denominator. So if you actually list out the sequence starting with n equals to 1, the first term is 1/2, then 2/3, 3/4, 4/5, and so on. Okay, so that's an example of a sequence. This goes on forever. Here's another one. So maybe just the list is given to you: 3/5, -4 25th, 5 over 1 25th, minus 6 over 6 25. And maybe there's enough of these sequences where the pattern is apparent. You might have to work out what the pattern is, right? So it looks like numerator counts up by 1, 3, 4, 5, 6, 7. It's also changing sign each term. So it's positive, negative, positive, negative, positive. When you have something like a sign changing sequence, thing that you could write down is like -1 to the nth power or -1 to the n plus first power, depending on whether you want to start with positive or negative. So since it's alternating signs, you might guess that the formula might include -1 to the n plus 1 in this case, because when n is equal to 1, it's positive. The numerator counts up by 1, so that's like n, except it doesn't start with 1, it starts at 3. So n plus 2 might be appropriate for the numerator. And then if you stare at it long enough, you might notice that denominator increases by a factor of 5 each time. So 5 to the nth power seems to work here. So you might have to, if you're given a sequence, you might have to reverse engineer what the formula might be. And that takes a little bit of practice. Okay, it might be something that's very difficult to give by a formula as well. So the sequence 3, 1, 4, 1, 5, 9. Some of you might recognize this as digits of pi. So there might not be a clean formula for nth digit of pi, but you could still describe it, right? So if you're asked to show what is the 127th term in the sequence, you can look it up on the internet and then be able to spit out a digit that satisfies the sequence. So this is perfectly well-defined sequence. Okay, another famous one is called Fibonacci sequence. So 1, 1, 2, 3, 5, 8, 13, 21. The way to get the next number is to add up the two previous ones. So 1 plus 1 is equal to 2. 1 plus 2 is equal to 3. 2 plus 3 is equal to 5. 3 plus 5 is equal to 8, and so on. So if you add the two previous terms together, you get the one in the next one. So this is called Fibonacci sequence. So you might specify the first two values, and then from then on, you could just write the nth term is the sum of the n minus first term and n minus second term. Okay, and that would generate this Fibonacci sequence. Okay, and once you have a sequence, you might care about is there a limit? Is it getting closer and closer to some certain number? Like if you look at the first sequence, you might guess that this is getting closer and closer to 1, although it always stays slightly below 1. You might care that like a Fibonacci sequence, this thing looks like it's gonna blow up to infinity. I mean, you're adding bigger and bigger number each time, so clearly it should blow up to infinity, but how quickly does it blow up? Is it exponential? Is it polynomial growth? And so on. So these are some questions that we could be asking. Okay, so let's talk about limit first, okay? So when sequence has a limit, here's what we mean by that. So we write down limit as n goes to infinity of an is equal to L if the following picture applies, right? So if you put a dot for each term in the sequence, okay, and make a graph, and let's say you suspect that it's getting closer and closer to a particular number L, then what you do is this. So what you do is you draw a horizontal line on L that you claim that the sequence is getting closer and closer to. And there's a test to see whether this limit exists or not. So the test is that you try to come up with a very skinniest band possible. By skinniest band, I mean, take the number L and you add and subtract a very small number, like 0.000001 or something. So you have a skinny horizontal strip centered at L, and ask the question, does the sequence eventually get trapped in this band? as you go to the right. So in this picture, it enters the band here, but it exits again here. But it re-enters the band here and never escapes after that. So if you can draw a line, and to the right of it, the sequence never escapes this skinny band, then it passes the test. And then he has to pass the test for no matter how skinny this band is. So no matter how skinny the band, eventually the sequence gets trapped in it. If that's true, then you write that, oh, that's the limit of the sequence is L as n goes to infinity. So that's what I mean by limit of a sequence. Okay. How do you compute it? Well, not too different from how you computed limits in Calculus 1 class. So for example, let's look at the first sequence we had in the previous page, n over n plus 1. We suspected that this gets closer and closer to 1, and we can prove it. What you could do is you can divide the top and bottom with this expression by n, right? So n divided by n in the numerator, we just get 1. In the denominator, n plus 1 divided by n is going to be 1 plus 1 over n. And as n gets larger and larger, 1 over n gets closer and closer to 0. So this term, it's kind of getting close to 0. What you're left with is 1 divided by 1 plus something super small. So the limit is equal to 1. Okay. And you might remember that you've done something like this in Calculus 1 class. Okay. So it's true, like you could use all the techniques we had in Calculus 1 and apply it to sequences to find the limits. Okay, so here's the theorem. So if you could talk about limit of a continuous function, or it doesn't have to be a continuous, but a function as x goes to infinity, where here it's a function, so x could be any number, not just integers. And if you can show that this function goes to L, and the function kind of traces the sequence. So imagine like there's a smooth function that hits all these dots. And if that function has a limit, then the sequence itself also has a limit, and it shares the same limit. Okay. So for example, let's talk about the arctangent function. So arctan is the inverse of the tangent function. And I find that most students remember how to draw tangent function. And if you can draw the tangent function, the arctan is the inverse of the tangent function. So you take this graph and flip it across y equals x line. And this is what arctan looks like. Okay, and because the tangent has a vertical asymptote at x equals to pi over 2, that means that the graph of arctan has a horizontal asymptote at y equals pi over 2. So this function has limit as you go to the right at pi over 2. So limit as n goes to infinity of arctan is going to be pi over 2. Okay. Let's see. Maybe we can look at limit like this. Limit as n goes to infinity of natural log of n over n. So natural log of n and n, they both go to infinity. So we have infinity over infinity. And if you remember from Calculus 1 class, there's a rule called L'Hopital's rule. So if you have infinity over infinity, what you could do is you could take the derivative of the top function with respect to n. So derivative of natural log is 1 over n. And you could take the derivative of the bottom function. So derivative of n with respect to n is equal to 1. And then you form a fraction of the derivatives of the numerator function and the denominator function. Note that this is different from taking the derivative of the quotient. You're not using the quotient rule. You're taking the derivative of the top and bottom separately. And then this thing gets closer and closer to 0. So the original limit also has the same limit. So 0 here. So this is called L'Hopital's rule. I'll write it down in case you need to review it in your textbook. Another technique that you might have used in Calc 1 class is squeeze theorem. So that might be helpful in a situation like this, where cosine of n over n, it might be difficult to work with this function, but you can notice that cosine of n, cosine is always between -1 and 1. So the largest it could be is 1, and the smallest it could be is -1. So it's this sequence is always trapped between 1 over n and -1 over n. But both of these are easy to compute, right? 1 over n gets closer and closer to 0. -1 over n also gets closer and closer to 0. And then the term in the middle has nowhere to go except for the same limit of 0. It's trapped between those two things, and they're both going to 0. So it's getting closer and closer. So by squeeze theorem, the limit as n goes to infinity of cosine of n over n is equal to 0. Okay. So these were some techniques that you might have used in Calculus 1 course. Okay. All right. So a useful fact that you might use is looking at what happens to a number as you take larger and larger exponent. One useful limit is if you have like a number that's between -1 and 1, so in absolute value, it's less than 1. Then what happens when you multiply by it each time is that the absolute value gets smaller and smaller, and each as n increases, so the limit goes to 0. So that's useful to know. The limit is 0 if it's between -1 and 1. If it's 1 exactly, 1 to the nth power is always equal to 1. So that's also a limit. If r is exactly -1, then it flips back and forth between -1 and 1. And it kind of repeats and never settles down to a single number. So that doesn't count as convergence. This is a divergent sequence. No limit there. So -1 limit doesn't exist. And also if in absolute value, if r is greater than 1, it gets bigger and bigger. If it's less than -1, then in absolute value, it's also getting bigger, and also it's flipping back and forth. So those don't have limits either. So all other cases, the limit does not exist, or D and E. So this is a useful piece of fact that you could use at any point. Okay. Another good thing to know is that if you know something has a limit and you are working with some continuous function like polynomial, trig function, or exponential function, or logs, or something like that, then the continuous function of the sequence is going to be the continuous function of the limit. So you can kind of, in some sense, you're putting the limit inside of the continuous function, compute the limit, and then once you got the limit, plug it back into the function. So that's a useful way to compute limits sometimes. So for example, if you have a limit of sine of pi over n, not sure how sine is affecting it, but I know that pi over n, that gets closer and closer to 0 because you're dividing pi by smaller and smaller. So you're dividing by a larger number, which makes the number smaller and smaller. So that the limit of pi over n is 0. So the limit is sine of 0, and sine of 0 is 0. Okay, I hope that made sense. Okay, so obviously I kind of went through quickly near the end because this is all review of computing limits in Calculus 1. So if you do need to review this, crack open those sections in your textbook and then review a little bit because we're going to be using them for the last couple weeks for the class. All right, anyways, this is a good place to stop. So I'll end the video here. I'll see you later.